Hello, everyone. This is the Daily Space. This is your host, Dr. Andres Plazas, and I want you to do me a favor. Can you hear me? Yes, it seems you can hear me. But as you can see, or as you can see and cannot see, I'm invisible. So I'm having some camera problems. But as long as you can hear me, then we're fine. Let's see if you can see the pictures that I have prepared for you today. That you can, it seems. So, yeah. Yeah, the camera is connected and I don't know what happens. So, sorry for that. I'm gonna check that after that, but well, let's get started. If you can hear me, just imagine this is your podcast and you just look at it, look at the images. Let's go back. So today, okay, for this is the daily space for Tuesday, August 14 of 2018, and as I said, I'm your host, Dr. Andres Plazas, and we're gonna talk about today three stories that I chose. One regarding, hold on a second. There you go. I got it. So first, we're gonna talk about neutron stars, and then I have two updates on two telescopes. One of them is the giant Magellan telescope, and the other one, the Arecibo telescope, that is getting a very nice upgrade. And the first story for today, as I said, has to do with stars, and it has to do with the role that protons play in neutron stars. So we know that the neutron stars are the smallest and densest stars in the universe. They're born out of the gravitational collapse of extremely massive stars. And of course, true to their name, they are composed almost entirely of neutrons. But there is a new study that appeared in Nature in the recent few days by researchers from MIT and Tel Aviv University. And this is a study that suggests that some of the properties of neutron stars that may be influenced not only by how densely the neutrons are packed in them, but also by a substantially smaller fraction of protons. So protons in a neutron stars make up just about 5% of a neutron star, but researchers have actually found that despite this small fraction, protons may play a larger role than thought, and because they carry substantially more energy than previously thought. Therefore, they may contribute to properties of the neutron star, such as stiffness or the ratio of the mass to the size, and even processes of cooling or other physical properties like that. So the researchers said that this finding may shake up the scientists' understanding on how neutron stars behave. Um, because they have found out, they think, according to their findings, that when you have a neutron a rich nucleus, you have a certain atom that is rich in neutrons. The protons move faster than neutrons, so in some sense, the protons carry more of the momentum of the average of the momentum of the star. So this is important because in general, backing up a little bit, the cosmological advantage of nuclei is not well understood, and so we think that the merging of two neutron stars is one of the main processes in which in the universe heavy nuclei are created, or heavy atoms are created, such as iron and gold. This study in neutron-rich nuclei indicates that we must reconsider the role played by this small fraction of protons in the neutron star and its impact on the nuclei creation process. So the researchers looked actually in data taken here in the lab, looked for signs of proton and neutron pairs of protons and neutrons in atoms of carbon, aluminum, iron, and lead. So this each one of these elements, they have a different atomic number. So that means that the sum of the protons and the neutrons in the nuclei are different, and as they increase in atomic number, the number of neutrons in these four particular nuclei increases. So we have carbon, aluminum, iron, and lead, and they wanted um, to see, or actually they found out that as the relative number of neutrons in an atom increases, so did the probability that a proton would form a energetic pair with another proton that with a higher energy probability than thought. So this is a trend that suggests that in objects with a high neutron density, like in a neutron star, the minority of protons carry a disproportionately large part of the average energy, and that's the main finding, and that came up as a surprise in this particular study. And one last remark regarding this story is that the researchers actually look at data that was taken about 14 years ago. So this data was actually, this study was based on data previously collected by a particular collaboration from data in a particle accelerator in a detector based at Thomas Jefferson Laboratory in Virginia. And the researchers said, of course, that the people at the time who were using the detector, they look for specific interactions, they measure a bunch of other properties, but of course, there may be other things that they might have not been looking at the time. So this is something that researchers do all the time, and even scientists, citizen scientists, or even the general public is encouraged to actually look at all the data sets and try to figure out new patterns with new analysis techniques like artificial intelligence, machine learning, for example, or deep learning or something like that. But in this particular example, they actually went back and look at this data set from 2004, and they were trying to study how the energy of protons correlated to the ratio between protons and neutrons in the particular nuclei of the elements that they analyze. So yeah, so this is what I have to say with respect to this story. And then, as I mentioned, I have two other updates with respect to other telescopes. So the first update that I have, so these are news coming from Pasadena, from the Giant Magellan Telescope Corporation. And they actually announced that they have started the excavation for the Giant Magellan Telescope that will provide the foundations for the enclosure of its site at Las Campanas Observatory in Chile. This is a telescope that is expected to see the first light as early as in 2024. And it has a particularity that has an the telescope will have an effective a mirror with an effective radius of 25 meters. And the way it will be achieved is that this main effective mirror is actually composed of a bunch of smaller mirrors, but each one of those smaller mirrors, there are 7 smaller mirrors that will have 8.4 meters of radius each one. And it will be housed inside a rotating enclosure that will measure about 65 meters tall, or about 22 stories tall, and 56 meters wide. So with the start of the construction of the permanent building at the site, the Giant Magellan Telescope is actually showing a tangible progress towards the completion. And this is great because this is part of a new generation of telescopes. For example, the extremely large telescope or the 30-meter telescope that are going to have a very high effective radius in their mirrors. But sometimes it is not always easy to start this type of constructions, of course, because of funding or because of political reasons or social reasons, like what is happening with the 30-meter telescopes in Hawaii. And these are, of course, very important discussions that need to happen. But it's nice to hear that in the Atacama Desert of Chile, things are going as planned by this Las Campanas Observatory. So yeah, one of the many sophisticated aspects of these telescopes is that it will have a very highly advanced system of adaptive optics. and they will offer images that are 10 times sharper than those offered by the Hubble Space Telescope. And it will help us answer questions, of course, like such as are we alone in the universe, or what is dark matter, what is dark energy, how did the first galaxies form, and we are very looking forward to the construction of these facilities that will provide us with more and better data to test our theories of the understanding of the universe. And then the last story that I wanted to tell also is related to another telescope. This is a good old one telescope. It's the Arecibo Observatory in Puerto Rico. So this is an observatory, it's a radio observatory, it's a dish that is about 300 meter in diameter, of about 1,000 foot diameter dish. It's currently managed by the University of Central Florida, and in this news they have reported that they received a grant from the National Science Foundation, a grant of about $6 million to design and mount a super sensitive antenna at the focal point of the dish. So in general, radio telescopes use specialized cameras, they are called receivers, to detect and amplify faint radio waves from space. Most of these cameras only see a small part of the sky at once, and this is a challenge when you have a radio telescope because the beam is too tiny. However, the grant that they have received in this particular case will be used to build a special type of receiver, which is called a phased array camera, a phased array receiver that has a particularity that uh, possesses an increased field of view. So that means that at the same time, when you point a beam on the sky, you're going to be able to see about an area about 4 times larger of what you could see previously with the current technology at the Arecibo Observatory. So one of the scientific objectives of the new receivers will be tracking objects such as pulsars. Um, for example, especially millisecond pulsars that a few decades ago helped signal the presence of gravitational waves, even before we had the direct detection of gravitational waves a few years ago. But of course, it will also help in the search for other in the scientific objectives, in the achievement of other scientific objectives, such as the search for extraterrestrial intelligence, or the detection of radio bursts, or study other objects such as quasars in addition to pulsars. And yes, this is reassuring to hear because, as we might remember, in September of last year, there were high winds associated with Hurricane Maria that caused the line feed, that caused some of the infrastructure of the telescope in particular to break and actually to fall into the primary dish. In particular, it was a 430 megahertz line feed that broke and fell into the primary dish, and it damaged about 30 out of the 40,000 aluminum pallets that they have, which is a small fraction, but still. But the good thing is that overall the damage inflicted on it was minimal, and the telescope observatory continues operations, and it's good to hear that even after 60 years they're still operating strong. It's for about 50 years it was the largest radio telescope in the world until a few years ago. There was a new telescope that had a 500-meter aperture that is called the 500-meter aperture spherical telescope, or FAST, in China. This is still one of the most powerful radio telescopes that we have, and it's great to see that it's getting all these upgrades and still working. So, yes, those are the stories that I wanted to share for today. I'm sorry that you cannot see me, but I hope you like my voice and that you had some fun hearing to me and looking at the pictures. And now I'm gonna go back and say hi to everyone in the chat and see what you guys have to say. So let's see. Let me look at the chat. It's usually in one of these windows that I can never find, and then I found it. All right. Hello, Kmore, Widow B. Who else is here? Adamal, DPI. Yes, you pointed out at the beginning that I had some technical difficulties. I'm sorry, but I hope you could hear me. It seems that was the case. Hello, Big J. And hello, Ed Thompson. Hello, Nightbot. Nightbot knows who I am and is telling you guys who I am. Hello, Larry. Scott. Honey. Hello. Um, you're right, Larry. Atomic number is not dependent on neutron, only proton. Yes, that's a Z. So I'm remembering my classes now. So it was denoted by Z. It just depends on the number of neutrons, and is the atomic weight that depends on the particles in an atom. I was thinking of that number that was denoted by the letter capital A. I'm remembering my chemistry and physics classes. Thank you for pointing that out. I hope it didn't cause confusion, but the story just wanted to look at those, in particular, four types of nuclei, like carbon, aluminum, iron, and I don't remember the other one, that had different ratios of neutrons to protons. And then when you bombard electrons to that particular nuclei, and then they wanted to see the distribution of proton pairs that resulted for that, the energy distribution, and they found out that this energy distribution depends on this ratio of neutrons to protons. And when you have an environment that has more neutrons, then they find out that they has that the the proton pairs produced had an energy higher than previously thought, and this could lead to a rethinking of what we know about neutron stars. What is the role of these energetic protons in the neutron stars? Do they make them brighter or spin faster? Is Hani is asking us. So I don't know the details of that, although they do mention in the press release that they may contribute to properties such as how stiff it is, the ratio of the mass to the size, and the process of cooling. I could see how it could contribute also to the process of cooling by a transfer of energy. Um, Hold on, you have more questions, and I'm coming back and read them. Ta-da. Are there protons in the outer shell of the neutron star bound by gravity or the nuclear forces? Because the electromagnetic repulsion should be enormous. I'm not sure about that exactly. Yes, I will have to check that and see what depends on the velocity distribution of the protons. And this makes me think, for example, of the plasma at the beginning of the Big Bang or before the creation of the CMB, where everything was in a plasma, and depending on the energy distribution of the particles and the velocity distribution of the particles, they were bound or not by the dominant forces. So I will have to go and check back the details of the environment of the neutron stars to try to get an answer to that precise answer. So sorry for that. Hani is asking us, what does Chile gain from having all these astronomy things built there? Are a lot of astronomers Chilean? That's a very good question, Hani. So in theory, in exchange for having all these astronomy facilities built in Chile, astronomers by law, Chilean astronomers get a 10% of the time in all the projects. That's my understanding. Still, it is the case that the number of astronomers in Chile is still way smaller than the number of astronomers from the majority of countries that fund these projects, which is the United States and European countries or Australia and those countries. So compared to them, the fraction of astronomers in Chile is very small. I think it was of the absolute number was of the order of magnitude of hundreds, which is not a lot. Compared to the rest of South America, Chile is doing great, of course, but that tells you the things of the scale of the difference for many different reasons, right? And this is one of the things that we need to try to work and try to make a more even place. But I mean, it is no doubt, I believe, I think that it is a great benefit that the astronomical community has worked out a way of building all these facilities in Chile. But it is a very important question to ask, what are they getting in return? And yes, I think they are getting something in return, but I think it could be more and it should be more. And hopefully things will improve in the future. Is our receiver in any way directional or is it fixed? I think I think you can steer a little bit, yes, with the receiver or the beam, but not a lot. I'm not that sure about that. I think that's you can still steer a little bit, but it's not a lot, and that's one of the reasons why it is important to have this increase in the field of view with these phased array receivers, which is a recently new technology that is being implemented in other places such as Australia, for example, where there are other types of more radio telescopes. Larry says that they like my voice. Thank you, Larry. He. I use they because I don't know, but I think you're a he. Sorry. Well, thank you very much for the compliment. Um, how far along is the Great Chinese Radio Telescope? I think it's already built. Let me see. I actually don't know, but the project actually started in 2011, the construction of the project of the 500-meter aperture spherical radio telescope, and it achieved first light in September of 2016, and currently is undergoing testing phase and commissioning. So, yeah, it seems it's going strong. Without knowing the details, no, you always find a lot of problems during commissioning, but that's what you do, commissioning and a first period of science verification. But yeah, hopefully they won't have anything crazy and things will work. How likely is it that proton-neutron pairing results can be applied to extreme conditions in neutron stars? That's a good question. They don't mention anything in the press release, but I believe that they took into account the energy distribution and the conditions of what they observed with this data from the laboratory and what you could find in neutron stars in order to do this conclusion, right? To arrive to this conclusion, but I don't know the details about that. I was very surprised to hear that there is as much as 5%. Yes, I actually didn't remember that either, but that's the case. With the Arecibo telescope and the other radio telescopes, do we have good coverage of both hemispheres? Yeah, that's a good point. I believe in the northern hemisphere we have telescopes, radio telescopes, such as, of course, the Arecibo telescope, the arrays in New Mexico, the Greenband telescope. And in the southern hemisphere, as far as I remember, we do have facilities in, well, as I just mentioned, in Australia, we as humanity, in Australia and South Africa, of course. Let me see. It is always not easy, right, to start one of these projects because well, in radio is good because you have longer wavelengths, and then you have different problems that in the optic you don't have to worry so much about the opacity of the atmosphere, but of course you have to take into account different technical problems. But then in addition to that, you have, if you want to build a project in a certain country of the world, you have to take into account other factors such as political stability and how remote the place is and stuff like that. Um, so we do have facilities in Antarctica, of course, in Asia, in China, mainly in India, Mongolia. I see like a higher distribution in the northern hemisphere, but it could be because there's more land in the northern hemisphere. But at the same time, there's also, of course, the money and the political stability in other parts of the world. Um, yeah, well, of course, the ones in Chile. So yeah, I would think that we have a pretty good coverage of both hemispheres. If you search Arecibo tour on YouTube, there is a quite good video of it. Okay, that's good. I haven't checked it out. I actually was there in Arecibo like 5 years ago. I visited Puerto Rico and it was pretty cool to be able to go there to Arecibo because it's very popular in even in the popular culture, right? I think the first time I knew about it was in watching the movie GoldenEye, which was kind of funny, but then I started reading more about it. What is the picture of the screen? I believe that's the picture from the facility from where they took the data in Virginia. But that's me speculating. I actually not that sure because I took that from the press release, and yeah, they don't have a caption there. Actually, they do have a caption, and that's the instrument at the Jefferson Laboratory Accelerator in Virginia. Yes, that's what it is. Yes, the square kilometer array, of course, in South Africa. Graham points out. Thank you. All right, everyone. It was a pleasure. I'm sorry you could not see me today, but I'm glad you could hear me and we still could have our nice conversation. I think I'm gonna call it a day for today. But as usual, thank you for watching, and in this case, thank you so much for listening and for tuning in. This has been the Daily Space, a production of CosmoQuest, created by the Astronomical Society of the Pacific. Please give us a follow if you like this show, or please consider subscribing. And we will be back tomorrow and every day of the week at 1 p.m. Eastern, 10 a.m. Pacific, and 6 p.m. London. Tune in tomorrow to see what's new in space and astronomy. Bye bye, everyone.